Hello, everyone. Thank you for coming to this talk, preparing for a future microservices journey using Wardley, including domain-driven design, Wardley Maps. The thing is that the $33 billion US is the estimated amount that the microservice architecture market was expected to grow as by 2023. And so that was done by a research report and by Market Research Futures, and they indicated some key trends that include this architecture market, and this was including loose coupling, deployment, and domain-driven design. So microservices was increasingly adopted by organizations worldwide, and also apparently also adopted in the future worldwide. So, and this is also confirmed by the InfoQ's Architecture and Design Trend Report, where they confirmed that microservices, including domain-driven design, were moving to the late majority of the adoption curve. But what needs to be highlighted is that the closely related topic of loosely coupled system is still far along the adoption curve. So there might be still some struggles coping with distributed system, also including microservices. And that means that we probably approach the trough of disillusionment of the Gartner hype cycle. So let's look at this, let's analyze this by looking at the journey to microservices. And our journey to microservices usually starts off with identifying good candidates for microservices. Good candidates for microservices are usually considering key concepts that following some principles. And these principles are high cohesion within a service and loose coupling between the services. High cohesion within a service is usually reflected by related behavior that shall stay consistent. Related behavior is reflected in domain-driven design by bounded context, your semantic boundary around your domain model. And when we introduce the journey to microservices, the microservice is supposed to own the state of their domain model. So for that purpose, we have to introduce data storage components. These data storage components needs to be configured and maintained and integrated into our services. Our microservices have to be deployed on some kind of service, preferably packaged as containers. We need to provide API for communication purposes. When other services would like to communicate with our services, they have to integrate this service API. We need to consider security aspects such as authentication and authorization and encryption. We need a service discovery to which each service is registered that allows services to be discovered by other services to connect to. As soon as multiple instances of our services are running, a load balancer is required that distributes the workflow and the traffic and the workload. And since our microservices are communicating over a slow and unreliable network, we need to design for failure to keep our system resilient. And we have to introduce stability patterns such as timeout handling and retries. And to recover from a failure that timed out. With retries, we have to make our operations idempotent so that its repeated call is leading to the same outcome. To preserve partial functionality when a failure occurred, we have to consider bulkheads. To protect our system against cascading failure, the circuit breaker helps us to isolate the failure. For event-driven service interaction, we need to provide a message broker to which the services can publish the message to, and that other services can subscribe to this message broker to receive messages. And for that separate components, we have to consider configuration, maintenance, and integration into our services. An API gateway as a single point of entry from the outside. And since our services not only consists of code, but also of configuration data, we have to make sure to provide centralized configuration management. We need to consider observability to generate a deep understanding of the health of our system. Yes, we have to set up a Git repo and a CI/CD pipeline. And last but not least, we also have to consider backup and recovery mechanisms for failed services and data components, and scaling our services, scaling them up and down as well. So, to build our services, we have to consider a lot of infrastructure and operational complexities. And also, with domain-driven design, they also come with a lot of new terms and takes a long time to grasp and understand those. So that could be very overwhelming, and that handling all these infrastructure and operational complexities by ourselves, including introducing domain-driven design with all their new terminology, could be so overwhelming that we could be very disillusioned after a while, and probably at the very beginning as well. So, and I would like to introduce Wardley Maps to highlight what's important to build microservices, what's the focus where we should focus on. And how many of you have heard of Wardley Maps before? Oh, you have a few of you. So, and how many have already evolved a value chain using Wardley Maps? A few hands. Okay, great. So, So the Wardley Maps were created by Simon Wardley, that's a researcher from the UK, and he has created this technique. A Wardley Map is a representation of, as a landscape of the landscape that the business is operating in, and is visualizing the value chain evolution. So what is a value chain? It's behind every user need there is a value chain, and it starts off with the first question: who are your users? Who are approaching you searching for help? And what are their user needs? What kind of problems do they have that they would like to get solved by you? And what are the components and activities that fulfill these user needs either directly or indirectly by facilitating other components and activities in this value chain? And how do these components and activities depend on each other? And what is their position in the value chain? So at the top, we have those components that are quite visible to the user, where your users are touching your system. And at the bottom, we have less visible components and activities to your users. After we have identified the components and its activities and the dependencies, we are taking this value chain and plot it along the evolution axis, going from left to right. Going from left, Genesis, where we have brand new things that have never existed before, to product, to custom build and product and rental, like off-the-shelf products or open source software, and commodity and utilities. And Wardley Maps come with some patterns and principles. And one pattern is that the map is never static but very dynamic. Everything evolves from left to right through the forces of demand and supply competition. And the movement of a component along the x-axis is determined by its stage of evolution. And you have to continuously adapt, otherwise you get overtaken by others. And while a component evolves from left to right, there are characteristic change. For example, going from the uncharted domain on the left, the uncertain, undefined, continuously changing, poorly understood market on the left, going to the industrialized market, the mature, widespread, well understood market on the right. And another pattern is that efficiency enables innovation. That means the industrialization of one component enables new features of existing products to appear, that other components can co-evolve, or that new components can emerge. And it's the genesis of new components that enables new user needs and creating future source of value. And that also comes with principles. And one principle is that you should use appropriate methods per evolution stage. So the evolution stage helps you to identify what components to build in-house, the components of the Genesis and custom build evolution stage, what components to use or buy off-the-shelf products or use open software for in the product and rental evolution stage, and what components to outsource to utility suppliers. And another principle is that you should know your users and focus on your user needs, because your user needs are the area of subject for what we build software. They are the why, the purpose of our business domain. But before we solve all your user needs, we have to understand the problem domain first, and that's where we come into the domain-driven design spectrum. where we obtain domain knowledge through intensive collaboration with our domain experts, where the domain knowledge is described. In terms of the ubiquitous language. And I also try to use Wardley Maps to mapping the strategic and tactical design patterns along the y-axis of the Wardley Maps landscape itself. So at the top, we could start with the strategic design patterns and going further down to the tactical design patterns. So we start in the problem space of the strategic design, and where we analyze our business domain, and where we discovering the subdomains, including its core domain. Then we can go further down into the problem space of strategic design, where we decompose our system into modular components, the bounded context, and where we map the interaction between those bounded contexts using context maps. When we switch to when we go lower down, we switch to the tactical design patterns, where we architect an implementation solution that fits closely as possible to our problem domain, and that provides building blocks implementing the domain model. So at first, we start in the problem space of the strategic design, and we are distilling our problem domain into smaller subdomains and discovering the core subdomain. And by distilling the core the problem domain into smaller subdomains, we are reducing the complexities. And not every subdomain is equal to each other, and some are more valuable to our business domain than others. So the core subdomain is the one that's essential to our business, and that's the one that provides competitive advantage. The core subdomain should be very hard to copy and imitate by our competitors, so it's supposed to be complex. And it tends to change often, and that's the one that we have to strategically invest in most. That's the one that we have to build in-house. So the core domain, they're supposed to go in the genesis and custom build evolution stage of the Wardley Maps. The supporting subdomains support the core domain, but does not provide any competitive advantage. They are quite simple, and they do not change often. And if possible, use off-the-shelf products or open source software. And if that's not possible, do not heavily invest in those ones if you have to custom build them. The generic subdomain is a subdomain that many large businesses have, like authentication and payment. And they are not core, and they do not provide competitive advantage, but without them, the businesses cannot exist. So they tend to be generally complex, but they have already been solved by someone else. So they do not change often. And you should focus on using or buying off-the-shelf products or outsource them to commodity suppliers. And when we go further down to the tactical design, then when we go further down to the solution space of the strategic design, we are trying to decompose our problem domain into modular components, the bounded context. And that's where we first start with identifying our domain models. At that stage, our domain models comes in different shapes. And for example, at first it starts with as the shape of our analysis model. And later it can result into our code model that is described in the terms of our ubiquitous language. And the domain model itself cannot exist without a boundary. And that's where the bounded context comes in. And these are potential candidates for our microservices. So, and the bounded context form comes with different types of boundary. So it forms a consistency boundary around our domain model to keep to protect its integrity, but also serves as a linguistic and semantic boundary where the terms of our languages are consistent inside. And also as an ownership boundary in terms of that one bounded context can only be implemented, maintained, and evolved by one team only, but one single team can own several bounded contexts. And also it serves as a physical boundary where we can have separate solutions, separate implementations per bounded context. And per bounded context, we can also apply different architecture patterns and different business logic implementation patterns as well. So let's start with an example after we have talked about all the theory. So let's create an example about that we would like to provide a software as a service conference solution and managing events and call for papers CFP. So who are our users that we are targeting? So we have the organizers of a conference and the speaker of a conference. And the organizer might have the user need to create an event and to start a CFP, call for paper, that the speaker would like to submit a session to. The organizer would like to evaluate the submitted sessions and would like to build and publish a schedule of the accepted sessions, and also communicate with speakers and sign in and sign up to the conference solution itself. The next step that we are going to approach is to discover the subdomain and splitting our problem domain in smaller subdomains, for example, and identify the core domain itself, because that's the one that we should strategically invest most. For example, by analyzing vision statements or collaborating with the shareholders. And so that's the core domain that we have to strategically invest most. And we drive our first domain models, and for example, that we can create for each subdomain its own domain model. And through the collaboration, through the knowledge crunching sessions with our domain experts. And the thing is that after a while, we figure out that some of the domain models could be related to different domain models as well. So CFP, speaker, and session could be related to several other domain models as well. And the problem is that this session, for example, can have different attributes for a CFP than, for example, when you schedule a session. When you schedule a session, it comes with attributes such as time slot and room, and it comes with business rules such as double checking if the room is not double booked, or if the session is not rescheduled or double scheduled. But these attributes, like time slot and room and business rules of double scheduling a session, is not relevant to the session submission, or to the session evaluation. So we have to adjust our ubiquitous language. We have to adjust our domain models a little bit, so that we have to add to change the ubiquitous language to evaluated session, to schedule session, and to proposed session, submitted session itself. So this is a strong indicator that these could be candidates for our bounded context that protects, that forms a consistency boundary around our domain model to keep our model consistent, and that the language is consistent within that bounded context. So another thing is that we can also share that one bounded context can only be owned by one team only, but one team can own multiple bounded contexts. And this enables autonomous teams working at the bounded context independently at their own pace with minimal impact across other teams. And as a physical bounded context physical boundary that bounded context serves, we can implement them separately and deploying them at separate artifacts. They can own their own data store, which is only accessible by its bounded context itself, but not by other bounded context. They can go and be maintained the source code into one Git repository and with one CI/CD pipeline per bounded context. And you can also apply different architecture patterns per bounded context. For example, that you have the layered architecture where you split your source code into layers such as presentation, business logic, and persistent, or the hexagonal architecture where it aims for separation of concerns and where it aims for creating decoupled software components that are easily connected to their software environment, or where we have CQRS, command query responsibility segregation, where we split our source code into read models and write models. And also, we can apply different business logic implementations per bounded context. For example, that we can implement one bounded context as a domain model consisting of the building blocks of aggregates, events, entities, value objects, and so on. And as a domain model, this implementation model, this pattern, is pretty well suited for the core subdomain because that's copes with complex business logic and complex business rule. Or we can implement a bounded context with the active record, where it represents a row in a database table and encapsulates the database access and applies business logic and data on top of it. So this active record suits best for simple logic and could be applied to the supporting subdomain, for example. Or transaction script, where we organize our source code or business logic by procedures, and where each procedure handles a single request from the presentation and fits best for very small applications with very little, with no complex business logic itself. So to give you an example, in our case, for the bounded context of the event management, we would like to provide a REST endpoint to create an event. And this endpoint is then taken by the event controller that receives the request, makes a syntactical check whether this request, for example, carries authentication data, if it carries an access token that contains the authenticated user. And this passes then the request to further down to the event application server as a port to the inner part to the business logic, which orchestrates use cases and manages this transaction, but it's free of any business logic. The business logic is implemented by the event model itself, which consists of the building blocks of domain-driven design, such as an event entity, which is identified by its unique entity event ID, and is composed of immutable value objects for name, description, period, and so on. And the event entity is served as an aggregate root that is designated as a public interface for this entity aggregate itself. So, and whenever some business logic is relevant, the event application service is calling the event repository to retrieve the aggregate from the underlying storage and applies the methods on the event aggregate and saves this back to the event repository, which is implemented by for example, MongoDB event repository, and saves it then in the MongoDB collection. So as one example, and we will evolve this later on. So to come back to the Wardley Maps, so since the domain-driven design copes with complex business logic, with complex business rules, it fits best in the core domain. It sits best for the core domain of subdomain of your problem domain. So it does not fit everywhere. So you should not apply domain-driven design everywhere. And so the supporting subdomain could cope with or could be implemented by business logic implementation pattern, which cope better with simple use cases, for example, active record. Or you can also focus on buying or outsourcing off-the-shelf products for the supporting subdomain or for the generic subdomain. So do not apply domain-driven design everywhere, because you have to focus on your core domain. That's the one that you have to strategically invest in most and innovate there. And I would like to change now the perspective a little bit and go back to the value chain itself. So we started with the user needs that are now fulfilled by the bounded context itself, and going further down through the architecture and business logic implementation patterns, but they all rely, the services themselves, the bounded context that we can use at microservices candidates, they all rely on data storage components. And they are less visible to us as a user, so they go further down. Since the session evaluation and also the schedule management also require some search capabilities, we would like to search for speakers or filter the sessions by topic, we might need to introduce a search engine component, which is then facilitating the session evaluation and the schedule management itself. And each of the services, including the search engine and the data storage components, they need to run on some environment where their software is going to be executed, the compute platform. And this compute platform is running on top of a virtual machine. So now we have plotted the value chain of our bounded context of conference of event management itself, including all the core domain and supporting and generic subdomains. Now we take this value chain and plot this along the evolution axis. So our first draft could look like this. So we are planning to build our core domain in-house, so that goes into the custom-built evolution stage, and use open source software for search engine, data storage components, for example, Elasticsearch and MongoDB, as described earlier. And we would like to have them packaged in a Docker container that is running on top of a cloud-hosted virtual machine. So the next question is, how can we map all the infrastructure and operational complexities that I was describing before? How do they could be mapped onto the Wardley map? And I would like to bring in this with 3 different perspectives, starting with a data perspective. So the activities that are necessary for the data storage and the search engine keeping the data itself is that as soon as we are running those open source products on premise, we have to configure, we have to take care of configuring them, we have to take care of providing backup, recovery, maintenance, including security updates and upgrades, scaling and metric gathering and monitoring aspects. And the next one that I would like to bring in are the service-related components and activities, and that each service is going to have in order to operate them. So this is consisting of centralized configuration management, scaling, recovery, distributed tracing, log aggregation, and metrics gathering, including monitoring aspects and security aspects as well. The next perspective I would like to bring in is the service interaction perspective. What are the components and activities that relates to that one? And we have 3 different service interaction types. So we have the request-driven service interaction, where our services are communicating directly with each other over the API, either sending a command for a state change or sending a query to retrieve some information from the other service. So the request-driven service interaction, for example, such as an REST API, is a pretty simple integration pattern, and which allows also synchronous processing, or to control the request flow when there is synchronous processing. But on the other hand, they come also with temporal coupling. So we also have to take care that when one service is down, we have to design for failure to keep our system resilient. And also is that we have to know the service location of the other service itself in order to call their API. With the event-driven service interaction, our services are not communicating directly with each other, but instead they are communicating via messages over a message broker. And this allows a loose coupling between those services and to flow the control flow on the receiving end, and also allows to easily plug in new consumers on the receiving end. But it comes with a downside that we also have to introduce a message broker as a separate component, which also requires additional activities such as configuration, backup, and so on. And with a hybrid service interaction type, we have our we have the request-driven and the event-driven service interaction combined, where our services are communicating via messages over the message broker. But only for notification purposes, so it only carries minimal data. And in case another service is requiring additional data from the other context, it does a remote query to the other context itself. So how does now our request-driven service interaction look like on a Wardley map? So since our services are now communicating directly with each other, we have to provide activities such as load balancing and service discovery in an API gateway for external requests itself. And since with request-driven, we are introducing temporal coupling, we have to design for failure when one service is down. And we have to introduce stability patterns such as timeout handling, retries, circuit breaker, bulkheads, and idempotency. And when we bring in the event-driven and hybrid-related components, when we bring in the message broker, for example, it requires also the same activities that we were introducing when we have to bring in the Elasticsearch and MongoDB database, when we run them off-premise, such as configuration, backup, recovery, maintenance, and so on. So when we look at this, we have a lot of activities that are related to the infrastructure that are at this stage in the custom-built area, which do not belong to our core domain. And we definitely have to evolve our value chain towards to the product and rental and commodity and utility evolution stage. And so the first approach could be let's use as much open source as possible. And for example, let's use, coming from the Java background, let's use Netflix OSS and Spring Cloud for circuit breaker and centralized configuration, or use Prometheus, Grafana, XStack, and Zipkin for the observability capabilities, such as metrics gathering, monitoring, health checks, log aggregation, and distributed tracing, or Nginx as some sort of API gateway, and load balancing, console for service discovery, and for the security aspect, like end-user authentication, for example, we could use Keycloak as an identity and access management provider, or we can also, for transport security authentication, we could use Vault's TLS certificate authentication. So what we have done right now is that we have moved some of the custom-built components and activities from the left, from the custom build, to the further right, to the product and rental evolution stage. And but at this stage, which is great, but at this stage is that they are still very visible to us as a developer, because we have to integrate these libraries in our bounded context, and also we need to configure. And need to also consider configuration, recovery, and maintenance for those components when they are running as services. So there's still a lot of things to handle, even though we have introduced open source. And the next approach that we can follow is, let's move out some components to closed-hosted services. For example, let's move out the message broker, the search engine, the data storage and the identity provider to to a cloud-hosted solution. So when we move them to a cloud-hosted solution, then we can also move some of their related activities to the commodity and utility, and we don't have to take care of it by ourselves anymore in terms of backup recovery and maintenance and scaling and so on. So these activities are now handled by the cloud provider that we don't have to take care on anymore. But what still remains custom built is the integration of these components and also the configuration of them. Another option is, or the next step in our evolution could be to offload some of the infrastructure and operational complexities to a container orchestration platform. So in a container orchestration platform, our microservices are packaged as containers that are running on top of a cloud-hosted orchestration platform that is running on top of a cloud-hosted environment. And the container orchestration is taking care of a lot of infrastructure and operational complexities, such as recovery, service discovery, load balancing, centralized configuration management, scaling, some monitoring aspects, log aggregation and health checks, and some sort of API gateway as well. So as a container orchestration such as Kubernetes, our containers microservices are running in a pod, which defines a group of one of more application containers, and these pods are can also include a volume, which is a shared storage for configuration data or secrets, also provide file system access. A service itself is an abstraction layer which defines a logical set of pods and enables external traffic exposure, load balancing, and service discovery. And each pod is running within a worker node, and a worker node is controlled by a master node. The nodes themselves are a working machine, which are typically running on top of a cloud-hosted which typically represents cloud-hosted virtual machines. And then Ingress enables the traffic routing from the outside of the cluster to the services inside our cluster itself. The deployment defines the desired states of how many replicas shall run of our pods and automatically replace any pod that has failed or became unresponsive. So how do they look like in a Wardley map? In a Wardley map, all the infrastructure complexities that the orchestration platform is taking care of are now abstracted away from us and moving further down. So we don't have to take care of them because the orchestration platform is taking care of it, such as service discovery, load balancing, and so on, which is great. But a Kubernetes cluster comes also with new primitives like pods, deployments, and services that I recently described, and a far lot more. So while a Kubernetes cluster or container orchestration platform is abstracting away infrastructure and operational complexities, it comes with new resources that they come to the scene that we now have to deal with. So a container orchestration abstracts away the complexities, which is great, but there is a trade-off that new resources and primitives come to the scene that we have to configure. So let's now say that we would also increase the operability by abstracting away the network application related concerns to a service mesh. And that we would like to have the timeout handling, retries, distributed tracing, security concerns, and circuit breaker, that these concerns are handled by a service mesh. A service mesh is decentralized infrastructure between our services that make our service communication safe and reliable. And they are running typically on, such as Istio, which I describe a little bit later, are running on top of Kubernetes platform. And they abstract away a lot of application networking concerns. So a service mesh such as Istio is logically split into a data plane and a control plane. So the data plane is composed of sidecar proxies that sit next to each service itself, and they take care of all service communication between our services. And they run typically on top of a Kubernetes cluster. So they come with built-in capabilities such as a load balancing and circuit breaker, and also health checks. And they control the request flows together with the mixer, which is taking care of checks the defined policies and also collects the telemetry. And there's also another component in the Istio service mesh itself, which is taking care of service discovery of our service, of our sidecar proxies, and also provides traffic management and the resiliency capabilities. And the TLS, the Citadel, is making our service-to-service communication secure by over TLS, and takes care of issuing and rotating the certificates themselves. So a service mesh, how does it look like in a Wardley map, is also abstracting away some of the application network-related concerns, so they move further down. We can now move these applications like retries, timeout handling, and so on. We can now move them out of our bounded context and move them to the service mesh, which is taking care of these application networking concerns. But it comes also with new primitives that we have to now to deal with and need to configure them. So while a container orchestration and a service mesh abstract away a lot of complexities, infrastructure complexities, becoming less visible to us as the developers, new primitives come to the scene that we have to deal with and to configure. And there might be also the desire, okay, we would like to, that's still a lot of things to handle, we would like to get it managed, to get this infrastructure fully managed by a cloud provider by introducing serverless. So with serverless, we get our entire infrastructure fully managed and provisioned. And with serverless, with the function as a service context, we are now dealing with a unit of work as a short-lived, small and fine-grained function instead of a container in the container orchestration. And these short-lived functions are triggered by a variety of events, such as HTTP requests, or database events, or scheduling events, or file uploads, and so on. And they are automatically scaling dynamically by usage. And you only have to pay per execution. So when a function gets idle, it shuts down and costs nothing. So, for example, AWS come with building blocks that you also have to deal with. So it also comes with its new primitives, as every other cloud provider as well. And with those building blocks, you can wire them together and implement AWS Lambda Functions to build your, for example, your conference solution. And how does it look like? So, for example, when we take the bounded context of the event management, we would like to create an event, and for that purpose, we would like to provide a REST endpoint. This REST endpoint is going to be exposed by the by the API gateway in the AWS context. And the API gateway triggers a Lambda function, which is implemented by the application API gateway adapter, which is then using the event application service, which now then also creates a new event model and passes this model to the event repository, which is implemented by the DynamoDB adapter, which saves it in the database. So, and as a next step, we would also like to activate an event. For that purpose, we also provide a REST endpoint, which is exposed by the API gateway as well. And this triggers this Lambda function, which is implemented by the API gateway adapter. And this takes this request and checks this if it's syntactically correct. For example, if it carries the authenticated user as an access token, for example, and passes this to the event application service. And this one then calls the event repository to load the event from the underlying database, and calls the activated method on that event model and saves it back to the database. And also, what it does publish an event that the event has been activated. For that purpose, the event application service calls event publisher, which is implemented by the SNS topic, a simple notification service topic publisher that publishes the event to an SNS topic. This topic, this message has been subscribed by the session handling bounded context. And for that purpose, we have an SNS topic adapter on the receiving end, and it triggers a new Lambda function that receives this event and calls the session application service to create another aggregate, the CFP aggregate, which is then going to be stored into the DynamoDB of the session handling bounded context. And the speaker would like to submit a session. For that purpose, we are also providing an REST endpoint, which is exposed by the API gateway, triggering another Lambda function, which stores then, in the end, the submitted session in the DynamoDB database. And the speaker would also would like to upload a profile picture. For that purpose, they are uploading the profile picture directly to an S3 bucket, and as soon as this profile picture has been updated, another Lambda function is going to be triggered that is being implemented by the S3 adapter, which takes the metadata of this uploaded profile picture and updates the metadata in the DynamoDB table of the session handling bounded context. So how does it now look in our Wardley Maps? So serverless, where we have our infrastructure fully managed and provisioned by our cloud providers, allows us to move a lot of components to the commodity and utility evolution stage of Wardley Maps, including a lot of the activities that are related to that one, because that's now the cloud provider taking care of it. Which remains custom built is the integration, in terms of that we have to implement the Lambda function, but also the configuration where we wire our building blocks together with the Lambda functions themselves. And there are also other serverless infrastructure providers available, and each of them comes with their own building blocks and with their own primitives that we have to deal with. And so there's also one thing, for example, a lot of concerns are sometimes mentioned to move towards serverless. That's, for example, the vendor lock-in. And for example, Knative is a Kubernetes extension that allows to provide serverless workflows on a Kubernetes cluster, which is abstracted away from you, and it could run anywhere. So to summarize is, at first we have to know our users and focus on the user needs, because the user needs, that is the subject area for what we build software. That's the why and the purpose of our business domain. And before we solve the user need, we have to understand the problem domain first, and work to collaborate with the domain experts, and also discover the subdomains to partition our problem domain into smaller subdomains, and also discover our core domain, because the core domain is the one that we have to strategically invest in most. And that's where we have to innovate, and that's the one that we have to custom build. And domain-driven design suits very well, I would say, for your core domain, because that copes with very complex business logic and very complex business rules. And for the other subdomain, you could go rather, when you build it when you custom build it, then with implementation patterns that are not as complex as domain-driven design, or prefer to use off-the-shelf products or open source software, or outsource to commodities suppliers. And that's also something that you should not custom build your commodities. That's something that you definitely have to avoid, because that shifts your focus away from building your core domain to handling all these commodities. Instead, identify and outsource the commodities to utility suppliers. And the industrialization of one component and the evolution of one component's and efficient provision enables the innovation of others. That means that new features of our existing services can appear, or that that a new bounded context can emerge that enables new user needs and creates future source of value. And also your current core domain, or the core domain of today, can become the supporting or generic subdomain of tomorrow. And for that, I thank you so much for your attention and your patience. Thank you.